In this lecture, we'll be talking about page replacement algorithms. This is the third lecture in a series of lectures on memory. Then this is going to be relevant to the virtual memory conversation. So when we think of page replacement algorithms, we need to answer two questions to begin with. The first question is, when do we need to bring a new page into physical memory? And the other question is, which page should we throw out? Now, when we have a page fault, meaning that the page is not in the physical memory, which is suggested by the valid bit in the page table being a 0, that would mean that we would need to refer to the disk drive to bring in the page from the disk into the physical memory so that we have the page. But when we do this, if the physical memory is full, meaning all the frames are occupied, then we would need to throw out a page. So we would need a systematic page replacement algorithm that is maintained by the operating system, and our goal is going to be to have the least number of page faults. So let's take a look at the need for this replacement a little bit more in detail. So for this conversation, we will have a physical memory with just 3 frames. So we have just 3 frames in the physical memory. And we are assuming that the current program references pages in this particular sequence. This is called a page reference string or a page reference sequence. So page number 7 is requested first, and then page 0 and all the way down in this list. So these are a total of 20 references that we have laid out in this particular pattern. Note that this is completely random in order to see how certain page replacement algorithms work for this same reference sequence. And because our numbers are ranging from 0 and the highest one is 7, it is very possible that we have a 8-page program that is running. So on the top of the slide, we have the page reference string that is the same one as we had for the previous slide. And at the bottom here, we are showing empty frames. So nothing is in the physical memory at this moment. So frames allocated are 3. And the first page that is requested is 7. So when we request 7, and we are writing it on top of the frame here, it's not going to be in the physical memory. It's empty right now, so we would have a page fault, and we would bring it from the disk. And when we do, it is going to occupy this particular frame. Then the second request is for page 0. 7 remains in the physical memory, but when we ask for page number 0, it's not going to be in our physical memory. So this is another page fault, which means that we would need to bring in that page. We have an empty slot, so page 0 can fit in one of the frames. So this carries over to the next stage. We are requesting for page number 1 next. So that is written on top of the frames here. And we had an empty slot, so it could fit in the third slot here. Now the physical memory or the number of frames are occupied by page 7, 0, and 1. And the next request is for page 2. So when we request for page 2, it is absent in the physical memory, which means that we would need to throw out one of these 3 pages to bring in page 2 into our physical memory so that the processor can use that page. So need to kick out one of these pages so that we can make room for page 2. So the reason we need this is because of the limited frame numbers, limited space in the physical memory. So the question is, which one should we throw out? Should we throw out 7 because it was used way too long ago? Should we throw out 1 because it was used just now? So what should we base this on? We need a systematic approach to throw a page out, or a page replacement algorithm. So I hope it is clear that we need some sort of a systematic approach to do this. So the simplest page replacement algorithm is first in, first out, FIFO algorithm, and it is easy to implement because it simply has a queue maintained by the operating system, and whichever page is at the head of the queue, it is going to be the oldest page, and we throw out the oldest page. So whichever came in first is thrown out first. The operating system is going to maintain that simple queue, and when we have a page fault, and if a replacement is necessary, and it is going to be necessary if the number of frames that are allocated are occupied with one page or the other, the victim page, or the page that we throw out or replace, is going to be at the head of the queue. So the most recent arrival in our example was page 2, request for page 2. 7 was at the head of the queue, so we are going to throw that out. So our new frame allocation is going to be for page 0, page 1, and page 2. So let's see how this plays out. So we have decided, or we have answered with FIFO algorithm who gets kicked out. It's going to be page 7 because it was first in to our queue. So that's our FIFO algorithm. So we decided to kick 7 out since it was the first one in. So when we kick out 7, 2 takes its place, and page 0 and page 1 continue to be there in the physical memory. Our next request was for page 0, and page 0 is present in our physical memory, which means that we don't need to change anything. We do not have a page fault, so we continue to have those 3 pages occupying the 3 frames. No change since 0 was already there. Our next request is for page 3. Page 3 is not present, so we would need to throw something out. We would need to throw out page 0 next because it was the first in after 7. So we decided to throw 0 out. 3 pushes out 0 since 0 was the first in because we have already thrown out 7. The next request was for page 0, which is unfortunate because we just threw out 0. And we would need to throw out 1 in this case because that was the first one in. So 0 pushes back in, we throw 1 out, page 1 out, and then our next reference is for page 4. Page 4 will replace page 2 because it is now the first one in. So page 4 goes back in there. 3 and 0 remain as is. We are requesting page 2 next. We are going to throw out page 3 to get 2 in, 3 out, 2 in, and then we continue the same thing. So next is 3. We are going to throw out 0 because 3 is not present. So notice we are having several page faults because every time we are throwing something out, that is due to a page fault. So there are several page faults, and I would expect FIFO to have the most number of page faults. So right now our sequence is 4, 2, 3. So the number of the page numbers that are currently occupied in the page physical memory are page 4, 2, and 3, and it looks like the first in is 4 right now because 4 came in, then 2 came in, then 3 came in. So the first in right now is 4. So for the next replacement, we would throw 4 followed by 2 and followed by 3. Alright, so let's count the number of page faults with these references. So we have gone through half of the list. We had a total of 20 page references, and we have gone through 10 of them so far. Those 10 have resulted in 9 page faults. Sometimes we were fortunate to have 0, for example. It was there in the memory and we didn't have the page fault, but the others we had to replace the page, meaning we had a page fault. So 9 out of 10, which is a 90% page fault ratio so far. Let's go and finish the sequence here. This is the second half of the same example. So next we are bringing in 0. So the reference is for 0. So earlier I said 4 was the next one out. So 4 goes out, 0 comes back in, and the same thing repeats. 3 is the next one requested, 3 is there, so no page fault, no change. 2 is next, no page fault, no change. 1 is next, so we would throw out 2 to get 1 in. The next request is for 2, so we would throw 3 out to get 2 in. And the next one is for 0, no page fault, it's already there, no change. Next is for 1, no page fault, it's already there. Next is for 7, we would need to throw something out. In this case, we are throwing out 0 and getting 7 in. 0, we still need to do it, so 1 will go out, 0 will come back in. And the last request is for page 1. We would need to throw out 2 to get 1 back in. So that is the complete example for 20 page references in a particular page reference string. So let's see how many total page faults we end up with. So it looks like we end up with 15, 9 from the previous half and 6 from this half. So a total of 15 page faults, which means we have about 15 divided by 20. So that's 75% page fault ratio or page fault percentage. So that's pretty high. So the next question is, can we do better? So obviously, if we had a better scheme, we could probably do better. So let's see what went wrong with this one. What went wrong with the FIFO algorithm? So if we see over here, as long as we were doing 701, that was necessary, and we had to bring those pages into our memory. But when the next 2 page references, 2 and 0, 2 we got in by moving 7 out, 0 it was still okay. But when we requested for page 3, we had to throw page 0 out, and that was a bad move because the next request was for page 0. So that was a pretty bad move because retaining page 0 would have benefited us, because page 0 was the next request. So that's the reason why that was a bad move. And we should have probably kept page 2 further down the sequence as well, because we threw out page 2 and then we brought something back in. So that is leading to too many page faults. So let's see if we can do something better. And we'll look at a few more algorithms to take a look at how we reduce that page fault ratio. But continuing with some complaints about FIFO, it turns out that even though you might increase the number of frames in the physical memory, you might have, for a certain string, for a certain page reference string, you might have an increase in the number of page faults, which is completely unexpected. I hope you guys see that if you increase the number of frames, in our previous example, the number of frames was 3. If we had 4, 5, 6 number of frames, if we increase the number of frames, then we can fit more pages in. So we should have less page faults. But it turns out that for a particular reference string or strings, it is possible that we might have an increase in the page faults. So Belody, it's called Belody's anomaly, and we can look at this by observing the number of frames on the x-axis, and we have page faults on the y-axis, and this is done for a particular reference string. So the reference string is 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. And as you can see, there are a total of 12 page references. So if we had just one frame, we would continuously keep throwing pages out, and we would have 20 page faults, each one for each page reference. And the other extreme is, what if we had 5 or 6 frames? Well, if you have 5 or 6 frames that can fit all the requested pages in them. So we will only have 5 page faults in that case because of bringing those pages for the first time. And once we bring in those 5 pages, we will no longer have any more faults. So 12 makes sense over here, 5 makes sense over here. However, what happens in the middle region? So as we increase the page a number of frames from 1 to 2, there is not such a big improvement. But when we go to 3 frames, we lower that page faults from 12 all the way to 9. However, when we go to 4 frames, we have an increase from 9 page faults to 10 page faults. A very important note here is that is because of this specific string. So Belody actually looked at those strings which caused that increase. And it turns out some strings do have that increase, and we are going to look at that over here. And Belody in 1969 established that the number of page faults can increase as high as a factor of 2. So in this case, you have 9 page faults. Belody claimed that the page faults could go as high as 18. However, in 2010, very recently, Fournay proved that there is no such bound. It can arbitrarily be very large. So for particular strings, when there is an increase in the physical memory, there could be an increase in page faults, which could be arbitrarily large. So it's unbounded. And the anomaly says page faults go up for certain reference strings when we have more frames. Alright, so that is a quick discussion on FIFO page replacement algorithm. We will be talking about other algorithms in the next video.